In this section, we want to summarize a few properties of limits. There are some important theorems. One of them relates the limit and continuity of a function. You can observe that the definitions are very similar, so it's not a big surprise that there is some connection. And the connection goes this way. Limit of a function for x approaching a is equal to L if and only if is equal to f of a if and only if the function is continuous at a. This can be illustrated by any continuous function. An example, f of x is x squared, and consider the point, say, a is 5. The function is polynomial, so it is continuous, and it looks like that. At value a is 5, the result is 25. And the function is nice, it is continuous, no jumps, no abrupt changes. The function is indeed continuous at the point 5. Actually, this function is continuous everywhere. It is continuous at 5, and according to the theorem, the limit exists and is equal to function value. So we can write limit of x squared for x approaching 5 is 25. So this gives a rule how to compute one kind of very simple limits. If the function is continuous, then the limit exists and is equal to the function value. So we just evaluate the function. So this is the simplest possibility. What possible complications there may be? If the function is not defined at a point, then the function value does not exist. But still, the limit may exist, but this does not hold, and the function is not continuous. One very surprising case is, even when fa exists, but is unrelated to the function values at close points, the function is not continuous and this does not hold. Consider the function g that is defined in this unpleasant way. It is equal to x squared for x is different from 5, and it is equal to 3 for x is equal to 5. You may like it or not, but this is a legal function. What about the graph? It looks like parabola with one important difference. For x is 5, the function value is not 25, but rather 3. This function is not continuous at 5, and this does not hold. So what is the function value and what is the limit for x approaching 5? G at 5 is 3, but limit of g of x for g approaching 5 is the height of the point to which the graph approaches from both sides when arguments approach 5, and this goes to 25. So even if the function value exists, it may be different from what we expect from observing the behavior of the function. So the limit gives us the important value that is perhaps more important than the function value itself. And a related theorem is, if we have two functions, let's f and g, such that they are equal for all x in some punctured neighborhood of A, then if at least one of them has a limit for x approaching A, then the other as well. So limit f of x is equal to limit g of x for x approaching A for x approaching A. In simple words, if the two functions agree in the punctured neighborhood, here and here, then the point towards the graph approaches is the same, so no big surprise. But this is completely independent of the function value of f at A and completely independent of the function value of g at A.